We're going to start this video with a challenge to you. I want you to pause the video and do example 3 on your own, okay? I want you to pause and classify the relative extrema and look at those extrema and say what you know about the derivative, okay? So go ahead, pause me now, and we'll go through it together. All right, so you should have been able to find that we have local maxima here at C and F. And we have local minima at A, at E, and H. Now, E looks a little weird, right? It's a corner, it's a cusp, all right? But it is the smallest around, okay? So we've done that. Everything else is, done. Okay, great. So blue are local min. And then we had the black was the local max. Okay. So for each of these, what do we know about the derivative? Well, look at all these points. Look at A. Look at C. Oh, not E. E's a little different. Look at F and look at H. These 4 points I have been like insinuating and telling this for this whole chapter so far. But notice that these 4 points, these all have horizontal tangent lines, right? Every single one of these points we pointed to, E's a little weird. We're not pointing there yet. Every one of these points is a horizontal tangent line. The derivative is 0. Okay? At these 4 points. But what about E? What's the derivative at E? Let's make it a little easier to see. Right? Well, at E, the derivative doesn't exist. Right? The slope from the left is different from the slope at the right. We said that we don't have a derivative at corners, at cusps, at discontinuities. The derivative doesn't exist at all these places. The derivative doesn't exist here. So derivative being 0 is a great thing to look for, but extrema can occur when the derivative don't exist as well, okay? And that's going to lead us to this concept of something called a critical point. Critical points are basically going to be candidates for local extrema. A critical point for a function is a point on the graph where the derivative is either 0 or undefined, okay? So that's what we want to look for, 0 or undefined. So all of these are critical points. All the ones that we've pointed arrows to are critical points. The derivative is either 0 or does not exist. It's undefined. Now the question is, are all critical points local extrema? And the answer is no. Critical points, I'll abbreviate that CP a lot of time. Critical points are candidates. They're the possibilities. But we could have a graph kind of like, right? This is the cubed root of x. This is a critical point. We have a vertical tangent line. The derivative does not exist. But is this the biggest around? No. There's bigger stuff on the right. Is this the smallest around? No, there's smaller stuff on the left. Okay. Similarly, what about a very similar graph? X cubed. We have a horizontal tangent line right here. This is a critical point. It's also not a local extremum, okay? So here are 2 examples of these are critical points, but not extrema. There we go. So let's get some practice finding them. And then we'll talk about how to tell. In the next video, we'll talk about how to tell if they are extrema without using a graph. So find all the critical points of this function. Well, remember the critical point is when the derivative equals 0 or doesn't exist. So to find a critical point has to do with the derivative. To find a critical point, we're going to need the derivative. So the derivative, we'll just use the power rule, is 3x squared minus 12x plus 9. When does this equal 0? When does this not exist? So first off, notice that this always exists. Right? This is a quadratic function. The domain is everything. There's no value of x that makes this not exist. All right. So we just need to find when is this derivative equal to 0? Well, let's set it equal to 0. And we're going to have to solve this equation. Feel free to review factoring if you need to, but we'll factor out a 3. What's left is x squared. This is our greatest common factor. What's left over when we take out a 3, it's like dividing out a 3. We get x squared minus 4x plus 3, and we're going to keep factoring. We need two numbers that multiply to positive 3 that subtract or that add to negative 4. We'll get x minus 3 and x minus 1. These will equal 0 only when each piece is equal to 0. So we get this. And we get x equals 3 and 1. And we are almost done, but not quite. We're looking for critical points. Okay. Points are x values and y values. Okay. So how do we find the y values for these points? Once we do that, we'll have our answer. Well, we plug it back in. Be very careful though, because we have two functions that we could plug it back in. This function is our slope function. The derivative tells you our slope, whereas this function is our actual function. That gives us the y value. Okay. So the y value when x is 3, plug that in and get it. The y value when x is 1, you can plug that in and get it. And I don't have my calculator prepared, but if you plug in 3, you get 27. You know what? Let's just pull up the calculator right now. All right. Yeah, our function is x cubed minus 6x squared plus 9x plus 2. And we want to find the function value at 3 and at 1. The y values are 2 and 6. So these are our critical points. Let's check our answer with a graph before we finish off the video. I said our critical point should be at 3, 2 and 1, 6. Do we have that? 1, 6. Yeah, that's a critical point. Horizontal tangent line. 3, 2. Great. That was what we said was a critical point. We did this all without a graph. I did use a calculator because I was lazy, but we didn't need to. And these are the only points on the graph with vertical or horizontal tangent lines or a derivative that doesn't exist. So we did it just as easy as that. Now, of course, we could use the graph to find out whether they're local extrema. The graph tells us that, yeah, this is a local max, this is a local min. In the next video, we'll talk about how to tell what these critical points are, if anything, because remember, critical points are just candidates. They don't guarantee an extremum. But we'll talk about how to figure that out without a graph. Sound cool? I hope so, because that's what we're doing next.